And welcome back. So now we have studied a bit of what the nucleus is, what is radiation, the common types of it, how does it come to be, and also how the decay happens. So now we know something called half-life, which is a characteristic of each nucleid, and it has to do with the speed with which the nucleus decays. And we know there's alpha decays, beta minus, beta plus, and electron capture. Now we're talking about the next step. What is really, we know decays happen because of energy, right? Now, what happens to this energy? This is an important question, right? So let's see here, just an example here. I'm just showing you, this is from the portable phone version of the isotope browser, I think they call it. Yeah, which I showed you. That's on the first class. I talked something just to show you why we use it. You'll have, for instance, for each one, you look silver 198, 108, and you have these two. You have the fundamental state and you have an excited state. And there's an important thing to notice here, just to round up the things we've said. You see that silver 108 has a 2-minute half-life and decays by beta minus. But there's also silver 108 metastable, right? Which has 438 years half-life. So you see that an excited state can have a half-life much larger than the fundamental state. It's not the most common thing, but it does happen. And in this case, you see that 108 metastable decays by capture, electronic capture, and beta plus, not by beta minus. You see, there's a trick here. Another thing is, for instance, if you go look at gold 198, right? Gold 198 has a fundamental state with 2.7 days half-life and an excited state with 2.2 days half-life, right? The first one decays by beta minus, and the second, IT, means internal transitions, mean gamma rays. So in this case here, you see there's no IT, so it never decays straight to this one. It only decays by capture or beta plus. This one happens the opposite. Yeah, this one decays only by internal transition to this one, right? And here, in fact, if you look at this one, yes, there is IT. Here you have a zoom in this one. You have 91% of the times it decays by beta plus or capture, and 8% it decays by internal transitions. It means that most of the times it decays by emitting a particle, right? Okay, one important thing for what we'll talk about here. In decays, remember I told you if we take atomic masses, they include the electrons, right? So there's one trick here. When you have an alpha decay, for instance, okay, the nucleus that is left, it has 2 neutrons and 2 protons less, so 4 units of mass less, but it has 2 extra electrons because the alpha particle went off without the electrons, so it left the same number of electrons that they were before, which means 2 more than this stable nucleus atom would have. And the alpha particle is missing 2 electrons, right? So in this case, when you sum up both things, there's 2 electrons missing here, 2 electrons plus here, so cancel out, no problem here. When we talk about beta decays, though, this becomes an issue. In beta minus, you have a neutron decaying to a proton, an electron, and I didn't talk of this before. There's an antineutrino here. Antineutrinos, they have no mass, they interact really weakly with matter. We tend to forget they exist, but it's just here to say I didn't forget it. So, if you think in atoms, right, it decayed. Now, the nucleus had Z protons, so there were Z electrons here. Now, the nucleus has Z plus 1 protons, but you still have Z electrons. So you have one electron missing here. And there's the electron that was emitted, right? So you have to remember to put this electron in your calculations whenever you do them. We'll talk about this in the next slide. Beta plus, it happens the opposite, right? The proton becomes a neutron plus a positron plus a neutrino, not an antineutrino, never mind. One thing to notice here, just as I told you before, right? The neutron becomes a proton, so a charge was created and the charge must be destroyed. You must compensate that. So total charge on this side is +1, -1, 0, and on this side 0. Here is the opposite. You have +1, this has nothing, so you have +1 here. So this is the decay. If you think, okay, number of mass is the same, but you lost one proton, but you had Z electrons here, meaning you still have Z electrons here, so now you're missing one electron here, right? And on electron capture, mostly the same thing. Just remember, you have a proton and an electron, meaning 0 charge. Here you have 0 charge. And what happens? You had here Z protons, and now you have Z -1, but you had Z electrons, and you still have Z electrons up here. So there's one electron in excess here, right? This will be important for the calculations we'll do now, because now we're talking about the decay energy. I told you the decay happens because of the mass deficit, right? Remember, we're talking about, so when you have a decay, you must release energy. And when you release energy, when you have a decay, let's say this is the decay, right? You're releasing energy. The mass before you only had this X, right? Or in the case of electron capture, there's the electron here too. And what you have afterwards, you have to remember to add up everything. You have Y, the new nucleus, and the particle that was emitted, being it an alpha, beta, or beta minus, beta plus. Okay, so mass before was this one, mass before is this one. But now we have to remember about the electrons. So, taking a look, as I told you before, when an alpha decay happens, there's 2 electrons that are here more than they should, but there's 2 missing here. So if we do the calculation, right here we should have the mass of the neutral helium less 2 electrons. And here is the mass of the neutral atom plus 2 electrons. Well, this cancel out, and okay, you have the mass of this minus the sum of these 2 masses, right? Okay, this is the energy released on the decay, on alpha decay. Remembering again, maybe I passed this too quickly. When you have a decay, you release energy because the mass of the overall things have reduced, meaning the binding energy per nucleon have increased, right? So how do we do that? Simple, as I told you, we have to calculate the mass deficit in the decay, meaning how much did it weight before, how much does it weight later, and we have a difference, right? Okay. Now, if we look at the other decays, life's not that simple, because I told you on alpha decay electrons did cancel out, right? On beta minus, we have a resulting atom with one proton more, but still have the same number of electrons, so it's missing one electron. So when we do the math, we have to use the mass of X, but this one we have to remember it's missing one electron, and we still have the mass of the electron, right? The electron that is emitted, the beta particle. So if you see, it ends up cancelling out, and on the beta minus, if you take a look, the mass of the electron disappears. So it's only this minus this, because this one cancels out with the electron that's missing. On a beta plus, it's the opposite problem, because now we have the resulting atom having one electron in excess, right? It lost a proton, now it has Z minus 1 protons, but still has Z electrons. So the mass of what's left before is the mass of Y plus the mass of an electron, because that excess electron is there still. And you still have the mass of the emitted positron, right? Which is the same as the electron in mass. So the Q, the energy released, will be, in fact, if you take a look now, there's two electron masses coming up here. It's not only this minus this, but now there's two electron masses. One from this electron and one from the electron that's now lost here. It's in excess, right? And on electron capture, once again, the same thing happens. It has one electron in excess, so what we had before, X and one electron, right? There's an electron here. And on the other side, you have, oh, it's missing, there's something missing here. No, it's right. It has one electron in excess, so what is emitted is like this. You have Y plus an electron, because there's one electron that's now is single there. And once again, it cancels out, and you just have to take care of this mass minus this mass. So, fast way to remember alpha, there's no transformation between protons and neutrons, they only are emitted. Calculation goes simply this minus this plus this. Okay? Perfect. For beta minus and electron capture, the electron cancels out. And on beta plus, the electron counts twice. Okay, I know it's quite hard to remember this, but that's the way we can do it, right? So in beta minus and the electron capture, the electron cancels out. No mass of electron required in calculations. For beta plus, the electron appears twice. Okay? So, what is this Q we're calculating here? It's the energy emitted in a decay, right? It's the energy that is released in a decay. And, well, I told you that nuclei, they decay in order to release energy to the universe and increase their binding energy by getting lighter, right? So, if that's true, this side here must be lighter than this one, because we need to release energy, right? So, when Q is greater than 0, meaning energy is released, Q greater than 0 means this side here is lighter than this side here, right? If that's true, you have diminished the mass and released energy, right? We call it an exothermic decay. This decay happens because that's what decays are bound to do, to reduce the mass and release energy. But if this guy here weighs less than the sum of these, remembering there's the electrons to take care of and everything, just talking about the nuclei here, then well, this, if the mass has increased, then we are not releasing energy. We should be consuming energy. We are not diminishing the mass, we are increasing the mass. That's not what decays are bound to do. So this decay will not happen. Why? Because there's no energy available for that, right? I have a system here. It has a certain amount of energy in the form of mass. I can release energy if I reduce the mass, but I cannot increase the mass because there's no energy for that, right? So when Q is smaller than 0, this decay will not happen spontaneously. And by spontaneously, I mean, okay, we'll talk somewhere later in nuclear reactions, then you have particles to bring that energy into the system, and these things can happen. But you have isolated nucleus here, it will not happen because it doesn't have the energy to do that. So, once again, Q greater than 0. This means you've released energy, diminished mass. This happens spontaneously. Q smaller than 0. This will not happen spontaneously. Okay, this cannot happen per se in real life. And just to tie things together, remember when I talked about stable nuclei, there were nuclei that were theoretically stable. This means that if you take every possible decay from this nucleus, Q will be, you study every possible decay, and for every one of those, Q is smaller than 0. This means that nucleus has no way of decaying. That's why we say it's theoretically stable. There's nuclei where you can find a pathway with Q greater than 0, possibly a very complex or something, so it has the possibility to decay, but you never observe it, probably because the energy is too low or because the path is too complex and it ends up not following that path. But that's the thing. We can say if a decay can or not happen by analyzing the energy balance, right? Things that we've shown before, but it's important to get you. One nucleus, it can decay by more than one way. Let's, provided that always have a positive Q, right? Or meaning, if there's two possible ways for a nucleus to release energy, it can go by both ways. Of course, the same nucleus will decay either one way or the other, but you have a large population of that. A part of them will decay one way, the other part will decay the other way. Some examples: europium-152, which is a calibration source we use a lot in the lab. It can decay by electron capture to samarium-152. This is 72% of the times, meaning I have 100 nuclei, 72 of them will decay by this route, and 28% will decay by this route, which is a beta minus to gadolinium-152. You see the same element, same nuclide, it can decay by two distinct ways, going to two distinct places, right? And each one has its own probability. Radon-211, it can decay by alpha decay to polonium, 27% of the time, and via electron capture to astatine, 73% of the time. Same goes for iodine-128, and there's several other examples. I just got 3 here just to show you. Iodine-128 can decay 7% of the time. It will decay to by electron capture to tellurium-128, and 93% of the times it will decay by beta minus to xenon. Okay? So important thing is all these decays here, they have a positive Q. Right? This one will not decay by alpha decay because Q is smaller than 0. This one will not decay by beta decay because Q is smaller than 0. Right? Now, we're conserving energy, right? This is one of the basic things of the universe. Energy conserves. So we have an X here, and it decays. And I've already said, okay, decays, they release energy. Okay, perfect. But now conserving energy, where does this energy go to? We have released, I don't know how many mega electron volts. Where does this go to, right? Well, first of all, let's say our nucleus was static, stopped here. When decay happens, just by kinetics, if I told you, for instance, this is a beta particle, a very energetic electron, it will go this way. To conserve momentum, you must have this nucleus recoiling too. Otherwise, you will not conserve moment, which is forbidden. So, first of all, a lot of it will go through energy here, right? Kinetic energy. When I say it's a very energetic electron, of course, it's energy that comes from where? From the decay, from the Q of the decay. And as I told you, if this one recoils, this one must. If this one is emitted, this one must recoil too. It's a consequence. Otherwise, you don't have conservation of moment. But then there's this one will be much less energy than this one due to conservation considerations. If you do math quickly, it comes quite easily. Difference of mass is too great, so usually this one gets a lot less energy. But there's also the excitation energy on this one, and this is very likely and very important too, because sometimes this particle takes a lot of the energy away, this one takes a bit, and there's still some change, and the change is left as excitation energy of this one. The process is too quick. Y doesn't have time to be produced in the most stable configuration possible, so it's still excited and it will decay. Right? Just to take a look at this thing here, we see that, just so you can believe me, if you have this, right, the total energy released will be kinetic energy for Y plus kinetic energy for B. I told you this is smaller than this, and the excitation energy of Y. If we take a look at momentum conservation, you see that the maximum kinetic energy of this one has to do with the mass of the heavy particle over the sum, and this has to do, for this is the light particle over the sum of those, meaning that the lighter particle has more energy and the heavier particle has less energy. Okay, and what happens? I told you, okay, you just believe me, I told you a lot of the energy goes to excitation energy on the product nucleus. And what is that? How does it manifest? Do you remember I told you what happens when you have a nucleus in an excited state? It will most likely decay by emitting gamma radiation, right? And that's what happens. So for instance here, it's cesium, the decay of cesium-137. It decays 100% of the times by beta minus in 30 years. You see here, these small arrows show the 3 paths it can. So sometimes, here we can say 5% of the time, right? This will decay straight to the fundamental state of barium, 137, and you have absolutely no change. You have no rest energy, no remaining energy to talk to, and no gamma rays. very small part of the times it will be produced in this state. But 95% of the times this will decay to this state here in cesium. And this state here decays by emitting a 662 kilo electron volts gamma ray. So 95% of the times the beta decay of cesium is followed by the emission of a 662 kilo electron volt gamma ray, right? And if we look another very common calibration source, which is cobalt 60, right? 100% of the times it decays by beta minus. You see now there's no chance this decay will take straight to the fundamental state. So every time a cobalt 60 source atom decays, nucleus decays, it will go to an excited state of nickel, not to the fundamental one. And negligible amounts here, 99.9% of the times this will decay to this state here, which then will decay most likely by the emission of 1173 and 1332. So most of the times, 99.9% of the times, it will decay by emitting this and then this gamma ray. And so that's why when we look at cobalt 60 source on some meter, we see two very strong gamma rays there. The other ones are very weak. If you take a look, this is 99.98%, this is 99.85%, and the other ones are less than 0.01%, right? So very weak transitions, the other ones. So remembering the excess energy, here you see you have the Q. This decay releases 2.8 mega electron volts, or 2800 kilo electron volts, which will be divided by the beta energy, a small bit for the recoil energy, and a lot for the excitation energy of Y. So you see, in the most common decay, it will emit a beta particle with 318 kilo electron volts, and 2,500 electron volts will be kilo electron volts will be on the excitation energy of Y. Well, not every time things are so simple. This is the decay of osmium 193 to iridium 193, and you see tons of gamma rays, stronger ones, weaker ones. So okay, sometimes life is not that simple. But just to show you, the arrangements can be absolutely simple, a bit less simple, or absolutely complex. But the excitation of energy on Y will always be emitted as gamma rays. Now, there are cases where there's, as I showed you here, in this case, 5% of the times there's no gamma ray emission, right? There's no excitation energy on Y. There's the case where there's never excitation energy on Y. That's the case of strontium 90, for instance, right? It always decays straight to the fundamental state of the next nucleus. Happens, but most of the times there are gamma rays. And gamma rays are important for us because gamma rays are easier to measure and quantify precisely. So usually what we measure are gamma rays, right? Alpha particles can be measured. We'll talk about this later on when we talk about detectors. Alpha particles can be measured with some precision, a lot. Beta electrons and positrons, they are very hard to measure precisely, and gamma rays are really easy to measure precisely. So that's often the radiation we measure are the gamma rays. So every decay may be, and generally is, followed by gamma emission. This is true for alpha, beta minus, beta plus, electron capture, right? There can be one or more gammas. Yes, there can be no gammas too. But in the cases where there are gammas, which are most common, you can have one or more gammas. But one thing that's important, if you have 10 gammas or 2 gammas, the sum of the energy of all those gammas have to be smaller than Q, right? Because the nucleus is produced in a certain state. It has a certain amount of energy to eliminate as excitation energy. Have some excitation energy will be released as gamma rays, but the sum of these gamma rays of each pathway here, right? Not the sum of all gamma rays, but here, for instance, this pathway, it goes here and then here and then here and then whatever. The worst part, this one that comes here and then here and then here. The sum of the gammas emitted in that chain is less than Q. Must be less than Q, because that was the maximum energy that was available, right? Now, just to check if everything's okay, let's see if actinium-225 can undergo alpha or beta minus decay. I have here the masses. So first, talking alpha decay, let's see, 225, it will lose 4 in mass, so it goes to 221, and it has to lose 2 protons, so it goes to 87. This is francium 221 plus an alpha, right? Let's see. Then for alpha, remember, electrons cancel out, just do the simple math. Okay, so it's this, and we have 5.93 mega electron volts of Q, meaning this decay can and will happen, right? Positive Q, decay happens. Now, oh, I didn't do the second part, leave you to do it. If for beta minus, it will come from here to here, and you have the electron masses there. But remember, beta minus, the electron mass does not appear, right? So it will be this minus this. And if you take a look, thorium-225 is a bit, very small bit, but it's a bit heavier than this one. So if you take this minus this, you get a negative number, right? So it will not undergo beta minus decay, right? So this is this class. Important thing here is to remember that energy is conserved. So energy is released when masses diminish. Energy is not released if masses increase, so masses cannot increase. And then this means that Q, the energy released in a decay, must be positive, otherwise the decay won't happen, right? Other important thing to remember are the tricky electrons. Essentially, on an alpha decay, everything is just simple mass of what was before minus the mass of what's left later. For beta minus and electron capture, the electrons end up canceling out. So you just have the mass of what was before minus the mass of the nucleus that's produced in the end. Forget about the electrons. And on beta plus, you have the electron that's just in excess there, will compensate, will sum with the other electron that is emitted, the positron. And then you have twice the electron mass appearing. So in a beta plus, you have what was before minus what's left minus 4, the 2 electron masses, right? So I think that's it for today, and it's important to remember that when any decay happens, alpha, beta, electron capture, you may have, and frequently do have, gamma ray emission just after that. just to give you the change, right? You went to buy something, there's some money that was left, and you have a change back. Gamma rays are that change. Okay? Thank you, and we'll see you again next class.